All right, welcome to Math 383, Complex Analysis. And so what we're going to be doing today, is we will be doing the Cauchy residue theorem. The Cauchy residue theorem. We'll also be talking about the accumulation theorem and the integration example of integrating 1 over 1 plus x to the n. If you know programs like Mathematica or the website Wolfram Alpha, you can actually calculate a lot of these things very easily by punching in lines of code. The question is, how are the computers doing this? And we'll talk about how you're able to get nice answers for problems like this. One of the big themes for today is how to recognize when two objects are the same. So this is a problem that you've hopefully encountered in other math classes, for two sets. Anybody know a good way to show two sets are the same? Bijection. So a nice one-to-one correspondence where each element goes and everything is hit. What's another way to show two sets are the same?
So they both contain each other?
They both contain each other. If everything in A is in B and everything in B is in A, then they're the same sets. So one of the themes is, how do we show that two things are identical? And then another one is, we're going to be talking about quantum integration. This is one of the math classes where most of the theorems you may not ever use again in the rest of your life, but the ability to do quantum integration is essential. It converts integration to algebra. This is progress. We would much rather do a little bit of algebra than try to do integration. And so one of the difficulties is finding the right paths. And I'm going to talk about the bring it over method. If anybody has another name for this, if you've seen this in a previous class, I'd love to know other names for the idea. And so just first a little terminology, zero pole, principal part, and residue. So if I give you some function, f of z is an z minus z naught to the n plus an plus 1 z minus z naught to the n plus 1 and so on. We'll assume that this series converges. And then if n is greater than 0, we have a 0 of order n at z naught. If n is less than 0, we have a pole of order n at z naught. All right, so standard notation, we call the principal part all terms with negative index. So, and then the pole or the residue is the a to the minus 1 term. So if I give you z minus 4 to the negative 3 plus 8 z minus 4 to the negative 2 minus 81 z minus 4 to the negative 1 plus 2 plus 4 z minus 4 plus dot dot dot. This part over here is the principal part. It has a pole of order or degree 3, and then the residue is negative 81. Okay, so it's not that hard to just pick off these things. It turns out that the residue is the most important part of what goes on. Does anybody have an idea why the residue is what really matters? Okay, that contributes how? Why? Excellent. So when you integrate z minus z naught to the n about a circle centered at z naught, the only contribution comes from the n equals negative 1 term. So because the only contribution comes from the n equals negative 1, that's why the residue is the most important part. And for many problems, the other parts don't really matter. Yes. I did not say anything about f being holomorphic. This is a general function where we have a series that converges. Correct. Absolutely. Now, if I wanted this to be holomorphic on a set including z naught, I can't have any negative terms because then it would blow up. But if you want to think of it as, I have this annular region I've thrown away just centered at the origin, And on that annular ring, I have an expansion like this. So then that's perfectly fine. The function is well behaved. And no, I'm sorry, it's in the Z0. And then in a situation like that, the function would be holomorphic in that annular region, but it would not be holomorphic in the larger circle containing it. Yep. Okay, so here are some theorems which we either have already proven or have essentially proven, but just not really explicitly extracted them. So the first is, suppose F is holomorphic in an open set containing a circle C and its interior, except for pole at Z0 inside of C. Then if we integrate F about that circle, we get 2 pi I times the residue of F at Z0. And the more general version is, imagine instead we have finitely many places where F is not holomorphic, then we just get a sum of the residues at those places. We've essentially proven this in all the arguments we've done. And we've talked about how instead of doing it on a circle, we could do it on a more general curve, so long as it has a well-defined interior and every point in the interior is part of my domain where the function is holomorphic. In terms of just the ease of writing, it's often nice to just say, I live inside a circle, I live inside a rectangle. But all we really need is the interior to be included. This means, of course, we have to be able to talk about the interior and the exterior, and technically what we need is the Jordan plane curve theorem. So if you want to do it in full vigor, read appendix, I think it's appendix B, and then you can do it in full vigor. Or if you want to say, henceforth, I shall only consider what is known as nice objects. So whenever you need to study something in mathematics, you say, we henceforth restrict to nice objects. Nice objects satisfy all the properties we need. Who are my physicists again? What is the definition of an ideal gas? An ideal gas is?
Ideal,
No,
perfect.
it is a gas that satisfies the ideal gas law equation. And what is the ideal gas law?
PV is equal to nRT.
The equation that governs the behavior of an ideal gas. So then the question is, well, which gases are actually ideal? So for us, it's enough to look at nice regions. Those are the only ones that are going to come up in practice. So again, just writing it explicitly, it's always a question of where do you want to put the 2 pi I? Do I want to put the 2 pi I with the sum of the residues, or do I want to have 1 over 2 pi I times the integral? Either way is fine. So imagine, I have, here is my curve. I'll do it a little bit more generally. Here's my curve gamma, and I will take a couple of points where things are bad. And then, the game we always play is coming in like this. And then again, what you'll notice is we're going to go through these circles in the clockwise manner, which we're not supposed to do. We always like to integrate in a counterclockwise. And so when we apply our results, what we get is the integral over the curve C of f of z dz is equal to the sum k equals 1 to n of the integral over, let's call it c sub k for the kth circle of f of z dz. So this is basically just using the formulas we've already had today. The only thing that's different is now we're going to actually evaluate the stuff on the right. What we've done before is we've said integrating our function f along gamma is the same as just adding those integrals. Now we're going to just figure out what those are. And so let's consider the integral over one of the ck's of f of z dz. So we can write f of z dz as f of z is equal to the sum. L goes from n to infinity of al I'll do a k to remind us that it's coming at the point k, z minus zk to the L. And now we have a sum and an integral. What do we want to do to the sum and the integral? Interchange. So now we use the integral of the sum is the sum of the integral. Why can this be justified? So if we have some type of absolute convergence, we're fine. The series converges. So what we can do is we can break up the series to the principal part and then the holomorphic part. And since the function, if you look at the sum of just the non-negative coefficients, this is going to converge nicely. It's going to be bounded. It even has a primitive, right? We can just integrate term by term. So we know the contribution of that is fine. So we can interchange the two. And now we're just integrating the terms that have a negative index. Well, the only one that survives is the 1 over, is the residue. Question?
Yeah, how do we know that this is right at the C of that series? Assume we have multiple right? Not more.
Okay. So it comes down to what do we mean by saying it has poles at these points? So if it has a pole, it has an expansion like this. So let's go back a page or two. So when I'm writing my function like this, if you have a pole of order, say 5, you start off with a 1 over z minus z naught to the 5th. If I multiply by z minus z naught to the 5th, I now clear it up and it no longer has a pole. And so what we're going to assume here in terms of what the language means is that if I multiply by z minus z naught to an appropriate power, I remove the pole and I have something that's holomorphic. Is that I have an expansion like this. So this is a good question. It's more of a definitional right now. But what I'm saying is I have something that has this expansion. We know holomorphic means analytic. We know that if you're holomorphic, then you have a series expansion.
Right, we're not holomorphic.
We're holomorphic except for having a pole. And our definition of having a pole is having a series expansion like this. So because of how we're defining what a pole means, I have the series expansion because of the definition. If this doesn't bother you, I strongly suggest you study ideal gases, governed by the ideal gas law. I still remember my freshman year, I was having so much trouble with one homework problem until I finally realized that the proof was by definition. And so depending on how you phrase things, sometimes the results are trivial. And so these are great questions to ask. We've set it up in such a way that by having a pole, I have a series expansion like this. Therefore, I know I have a series expansion because I've told you I have a series expansion. For proof, see some work of Professor Jones published by the Department of Redundancy Department. Okay, yes.
I have another question about that.
Yeah.
So, we know that it is that the poles are in that format, but we don't know exactly like if the input right? So
Well, no, I have a different expansion in each one. That's why I'm using a sub LK.
no.
That's why I put in the K. Is the coefficients do not have to be the same at each expansion. Each expansion has its own sequence.
That is different with this holomorphic, right?
Well, I mean, if I were to do a series expansion for holomorphic functions, depending on which point you do, your coefficients are really coefficients of that point. I could write, instead of ALK, I could do AL of the point ZK. But these are the coefficients that come from expanding about ZK. I could also write that there's lots of different ways of writing the notation. I need some way to denote the fact that these terms are coming from my choice of where I expand. And if I'm choosing to expand about K, I can either put in a second subscript as a K or say I'm evaluating this. And notice that a negative 1K is a negative 1 of ZK, and that's going to be the residue at the point ZK of F. And so now when I do my integration, the integral of a sum is the sum of the integrals. The only thing that matters is the principal part. The only thing that matters from the principal part is the negative 1 term. And what we've shown is that the integral is just 2 pi I. So we get that the integral over ck of f of z dz is just 2 pi I times the residue at zk of f. And that finishes the proof. So we just add all of the ones. Now it's important to note that we only have finitely many poles here. We do not have infinitely many. And you could ask me, what would happen if I had infinitely many? We'll talk a little bit about some issues like that. Okay, so here is the motivation for the next part of the lecture today. Beautiful theorem. Suppose f is a holomorphic function in a region omega that vanishes on a sequence of distinct points with a limit point in omega. Then f is identically 0. So another way of interpreting this is corollary. If f of z equals g of z for the sequence, zk, k goes from 1 to infinity, and the limit as k goes to infinity of zk equals, say, z star is in omega, then f is identically equal to g. So if two functions agree on a set of points that accumulate, then they have to be the same function. And this just comes from looking at the function f minus g, which is now 0 on a set of points that accumulate. This is completely different from real analysis. In real analysis, I could give you the function f of x is, say, x cubed sine 1 over x. And just to be clear, we'll make f of 0, 0. This function is going to be 0 on a set of points that accumulate at the origin. This function is even going to be differentiable. But this function is not identically 0. So zeros accumulate at x equals 0, but not identically 0. So this is yet another illustration of just how different complex analysis is than real analysis. You can't have a result like this in real analysis. It's actually not that hard to come up with a counterexample. If you've taken an analysis class, you might have seen the Weierstrass continuous but nowhere differentiable function, or there's other generalizations of this where you have to do a little bit of work, but you can come up with a function that's discontinuous everywhere. I'm sorry, that's continuous everywhere, but nowhere differentiable. It's not that hard for me to come up with a function that has a sequence of zeros that accumulate, but is not identically 0. So why is this so important? Well, one of the biggest questions we have in mathematics are, when are two objects the same? So interestingly, I was talking about Kepler's laws of planetary motion in my probability class today. And when Kepler was trying to prove, what are the motions of the planets, and he was looking at the data, at one point he was working on the orbit of Mars, which is a really interesting problem, because if you look at the data from Earth, at one point it looks like Mars stops, goes backwards, and goes forward again. How do you explain this retrograde motion? At one point he said, I've just proven it follows this form. If only it was an ellipse, I would know what to do. It turns out it was the equation of an ellipse, but it wasn't the standard formulation of the equation of the ellipse. So when he was just bemoaning the fact that if only it was an ellipse, instead it's this damn object, it was an ellipse. He had it, but he didn't initially recognize the algebra. This is the same as the Rubik's cubes that I sometimes bring in and show, that it's the same cube, but they try to display it in a different way. How can I tell when two functions are the same? One way is if I can show that they agree on a set of points that accumulate, an infinite set of points. This is going to be very important for applications in probability. When can I uniquely determine a probability distribution? So for those of you who do any random matrix theory projects with me, this is a great question. When do the moments uniquely determine a probability distribution? Equivalently, when do the Taylor coefficients uniquely determine a function? We saw that you can have a function whose Taylor coefficients are identically 0, which is a huge shit, right? That means if I give you a function, you cannot uniquely determine it by just knowing its Taylor coefficients. I could add 1,701 copies of my painful function raised to the 24,601st power, the e to the negative 1 over x squared function. and it has all of its Taylor coefficients 0. So the Taylor coefficients do not uniquely determine the function. This is going to give us a way to uniquely determine things. And to rigorously prove the central limit theorem, this is a great way to do it. It's not enough to have the moments agree at the integers. You need to have a sequence of moments that accumulate to get uniqueness. For those of you who've done physics, there's a great paper, Can You Hear the Shape of a Drum? It's very similar to questions like that. All right, so this is the philosophy of why we care about this. Now it's time to do it in practice. How do we prove this? So as always, think about what do we know? Well, we know the function f is holomorphic in a region. It has a sequence of zeros that accumulates. Yes.
I have like no intuition as to why. Like, is there any like I don't know way to understand this? Why?
Yes. So you just asked, is there any intuition? And the answer to your question is yes.
Okay.
So I think the best is to do the proof and then see what the proof shows as to why. The main idea is I was going to ask, as soon as I tell you the function is holomorphic, what do you immediately know about it? It's analytic. So that's the difference. In complex, holomorphic implies analytic. And so that's the intuition, is that as soon as I tell you I have an analytic function, maybe the result is true in real analysis. If I restrict myself to analytic functions, functions that are given by their Taylor series. And notice that my counterexample here is not complex differentiable. And so I need something that's going to throw out cases like this. So again, complex analysis, the reason we have such miraculous results is we greatly restrict the set of objects we study. There are stories of someone who in their thesis proved a certain class of functions have certain properties. And in a few years after, so I think you've heard the story? Yeah. So a few years after their thesis was published, somebody proved that the only functions in this space are the constant functions. And most of these results were already known about the constant function. You know, the constant function, it's really not that hard to prove it's infinitely differentiable, for example. But with the definition that they were working on, it was a highly non-trivial proof to show that these functions had these properties. So when you're working with the space, the first thing you want to ask is, who's in the space? And so the whole point of this is complex analysis is so restrictive on what it allows to be differentiable that you're going to see wildly different behavior. If I were to ask about the average math ability of a Williams student, and I want to just choose somebody at random, and I choose somebody from a graduate level complex analysis class, do you think this is a good sample point for Williams in general? If I do, I will get, wow, everybody at Williams has taken real analysis. So if I restrict myself to only students in complex analysis, boy, am I going to be misinformed about what a typical Williams student looks like. It's the same thing when we look at complex differentiable functions. Our intuition is just terrible because we're used to considering so many different types of functions. Complex analysis, nope, not going to look at it, not going to look at it, not going to look at it. Feynman is great on this. He has passages in his stories where he talks about how he can always tell if a theorem is true or false. As the mathematicians start giving him things, he starts visualizing in his mind. Okay, now I'll pretend it has tentacles coming out. Okay, from what you said, the tentacles are orange on this side and red on this side. He'll have this picture in his head trying to visualize what they're giving him. And he'll try to interpret it like that. And the more restrictions you put on, the fewer things you have available. So because we're holomorphic, that means we're analytic, that means we're given by our series expansion. So near z star, we have f of z is equal to an z minus z star to the n plus an plus 1 z minus z star to the n plus 1 plus dot dot dot. So here is z star, and I have to have a sequence of points that's accumulating towards it. Right. There could be other points as well, but I have to have some sequence of points that accumulate. So along that path, my function is 0. And it has to be 0 at z star. So why is f of z star 0? Yes. Yeah, it's just continuous. I don't need to use any fancy results from complex analysis. By continuity. As f of z star is just the limit as k goes to infinity of f of zk, and each one of those is just 0. So we have a Taylor series expansion. We know it has a 0 at z star. What can I deduce about n? So what do I know about n? It's positive. N has to be at least 1. It can't be negative or I'd have a pole that blows up. It can't be 0, or then I would just have f of 0 is equal to a naught. So I know n has to be greater than 1. So as n is greater than 1, I can write f of z as an z minus z star to the n times 1 plus an plus 1 over an z minus z star plus dot dot dot. Yes.
Still n greater than equal to 1.
Yes. If I wrote yes. So I'm just pulling out z minus z naught to the n, and I'm pulling out an. We know an is not 0, so I can do this. Well, as z gets very, very close to z star, what can you tell me about this part over here? If z minus z star is small, this sum is so what can you tell me about that infinite sum if z is very close to z star? It has to be small. Quantify small. Small relative to what number? One. The sum is small relative to 1. The series converges. So explicitly, there exists a delta, or for all epsilon greater than 0, there exists a delta such that if the absolute value of z minus z star is less than delta, then the sum is going to be less than epsilon. Because I have an analytic series. The series converges. If I take z equals z star, I get 0. So because the sum converges, it converges inside its radius of convergence. If I move just a little bit, it can be small. So what that means is that 1 plus this is always going to be greater than 1 minus epsilon if we're sufficiently small. So 1 plus crap is at least 1 minus epsilon if z minus z star is less than delta. And so I'll do like the absolute value. Because I can force that sum to be at most epsilon in absolute value, worst case is if it's negative epsilon and I drive that sum down to 1 minus epsilon. But remember, we have, here is z star, and we know there's supposed to be, an infinite sequence of points, converging to it where the function is 0. I can't have any other zeros close to z star. Contradicts infinitely many zeros near z star. Because if we're sufficiently close, the 1 plus that sum has to be positive. in absolute value. Right, and that, the absolute value of the 1 plus everything else is at most 1 minus epsilon. Yes?
But aren't we multiplying by a n?
We're multiplying by an z minus z star to the n,
Oh.
which is non-zero,
Okay.
right?
Yes.
This part over here is only 0 at z equals z star. And so we can't have any 0 other than z star sufficiently close to z star. This forces the zeros to be isolated. Zeros must be isolated unless the function is identically 0. But we're assuming the function is not identically 0. When we're writing a series expansion like this, I'm writing it as an z minus z star to the n. So what we've now shown is that if you have a point of accumulation, the function is 0 in a small disk about the accumulated point. And so what really is going on now is, here is my omega. Here, a bunch of points. Here, it's accumulating down there. And so I now know in some disk over here, it's identically 0. And now what we want to do is we want to go from it's identically 0 here to it has to be identically 0 in all of omega. Yes.
Verify why is
In absolute value. Because when z is very close to z star, the infinite sum is going to be extremely small. I can get it as close to 0 as I want.
in the bracket
In the bracket at top.
very top of the right.
Yes.
1 plus.
Well, but I'm saying it could be a signed quantity. Right? So because it's a signed quantity, the worst case for me is if it comes in as a negative epsilon and tries to drive down the sum as much as possible. So the worst case is when it comes in as a negative epsilon. This is similar to when we were looking at 1 over z squared plus 1 and looking at on the semicircle. What is the largest that could be an absolute value? The largest is r squared minus 1. So it's very similar here. So if I have this sum, basically what we're saying is that sum is close to 0. So 1 plus that can't be 0. So because of that, we have to, we find that the zeros have to be isolated. So we now know that the zeros are isolated, or conversely, that the function is identically 0 in a small ball. Now that we have it's identically 0 in a ball, we want to expand outward. Due to time, I want to make sure we have time to do some integration examples. So I'm going to refer to the book for the topological argument. To now use topology. This is connectedness. C book to expand to all of omega. But again, from all the stuff we've seen before, to have a function that's identically 0 in a ball, but not being identically 0 everywhere seems strange, but you have to formally deal with that. And so the book has a way of pushing things outward. And then from any 0, you can push things outward even further. All right. And if people have questions about that, I'm happy to talk more about that. But I want to make sure we have the time to do an example in full detail. So this is the bring it over method. This is pulled from a probability book I wrote a few years ago. What I want to do is I want to talk a little bit about ways to solve some integrals. So here the integral is the integral from 0 to pi of e to the cx cosine x dx. And again, all of this stuff is on the slide, so you're welcome to just watch this. The slides will be posted. If you try to integrate by parts, if you integrate by parts once, I get the integral is equal to some boundary terms which vanish, and then an integral of e to the cx times sine. Well, that's similar to what I started with. I started with an e to the cx times cosine. It suggests do it again. And if you do it again, you now have some constant outside from the boundary terms. And then you have an integral of e to the cx cosine x. Ah, that's what I started with. And it has a coefficient. It has a coefficient of c squared. So I bring this over and I can solve for I. And so as long as c squared is not -1, we win and we can solve for I. So this is wonderful. So the way we evaluate this integral is we never actually evaluate the integral. We just evaluate a bunch of boundary terms when we integrate by parts. And then we say, well, a full copy of our integral plus c squared times our integral equals this part that we know, therefore we know the integral. And the actual value is, I think c e to the pi c plus c over c squared plus 1. And then you can use some tests to make sure that there are no typos. I think there was originally a typo in a draft version of the book. You might have seen this with a geometric series. If g of x is 1 plus x squared plus ... This is g of x is 1 plus x times g of x. So 1 minus x times g of x equals 1. So g of x equals 1 over 1 minus x. So if these steps are justified, here's a proof of the geometric series formula by using this idea of bring it over. So this is a great way to evaluate a bunch of integrals. You never actually evaluate the integral. You show certain combinations of the integral is something that's known. Therefore, you can deduce what the integral is. So this is yet another example of integrating without integrating. Okay, so mathematicians are lazy. Thank you. I don't really bother remembering that because I'm pretty sure somebody will remember it. Thank you. So we're lazy. This is something to be proud of, right? Let other people kill themselves doing things again and again and again. So we are going to bypass hard integration. So I'm going to look at the function integral from 0 to infinity 1 over 1 plus x to the n. So you were asked to think about this beforehand. What might be hard? We did before the integral from minus infinity to infinity of 1 over 1 plus x squared. Why am I going from 0 to infinity? Why don't I want to integrate like 1 over 1 plus x cubed from minus infinity to infinity? Yeah. When I take 1 over 1 plus x cubed, if x is -1, it blows up. It is not good to blow up on the line of integration. Then you have to be really careful and deal with that. Now, if we're trying to think about these as probability distributions and we're trying to figure out what's the normalization constant, well, I clearly don't want to have a place where I'm blowing up. So it's not unreasonable to assume that x is greater than 0. If I truly want to integrate from minus infinity to infinity, I can do that if n is even. Well, if I could figure out the integral from 0 to infinity, I can just multiply by 2. So it's really not that big of a deal to restrict to something like this. So the question is, how do we handle something like this? Well, one thing is you can go to Mathematica or Wolfram Alpha, type in integrate 1 over 1 plus x to the n, 0 to infinity. To help Mathematica out, I make the assumption that n is greater than 1. That helps to know that n is a real number and that this is going to be integrating over a region where it converges. And Mathematica will actually output the answer. I'm not going to show you what the answer is, but there's a beautiful, simple, closed form answer, a nice function of n. How does Mathematica know how to do this? Let's talk about integrating. So we have the function f of x is 1 over 1 plus x to the n. We have to complexify it. Anybody want to guess? You may be wrong, but it should be really natural what you should guess here for the complexification.
1 over 1 plus z to the n.
Yes. The only other acceptable answer would be 1 over z to the n plus 1. And that is also acceptable. You think I'm just trying to be a smartass and funny, but actually, there is a justification for writing it as z to the n plus 1. Because we're thinking about eventually factoring it. And so if I write it like this, I'm writing the highest term first. But it's the same function. This is the natural thing to look at. So when you look at the function 1 over z to the n plus 1, we can choose, do we want to try to do this for general n? Do we want to try to do it for small n? It's often a good idea to do small n first and build intuition. So the book, or at least the example I did in the previous video, does n equals 3. I'm happy to do n equals 3 or n equals 2. Do people have a preference? Yes. 2? Even? Okay. So let's do n equals 2. And what's nice is if we do n equals 2, we can compare this to the Cauchy distribution. Right? So when we look at 1 over z squared plus 1, what are the dangerous z's? At z squared plus 1, that's going to be z minus I, z plus I. So we have poles at I and minus I. And then we need to figure out what the residues are. If we were doing this with n equals 3, we would just have to factor z cubed plus 1. Is that hard? No. What about if we took n equals 5? Is it hard to factor a quintic? I'm sorry? So I can give you a quintic and you'll factor it for me. General quintic. Oh, not a general. So, but this is a very special quintic. This is z to the n plus 1 equals 0. So that means z to the n equals -1. So the general case is not so bad. And we need z to the n equals -1 equals e to the pi I. Right? So what would the roots be? Yes. What's the first one? The first root would be e to the
just pi over n.
okay, pi I over n. And then the next one would be e to the pi I over n plus 2 pi I over n. Because when I raise that to the nth power, I just get 1. And then the next one would be e to the pi I over n plus 2 times 2 pi I over n. So I can write down all the roots without too much trouble. So this is a really nice polynomial to work with. We luck out. Now, we need to calculate the residue. Okay, so if we want to calculate the residue, we have f of z is 1 over z minus I, 1 over z plus I. And let's do things at the point I. The point minus I is going to be similar. We'll do it at I. We'll study at I. Now, 1 over z plus I, what kind of function is this at I? It is a holomorphic. So I can write that as f of I plus f prime of I z minus I plus f double prime of I over 2 factorial z minus I squared plus dot dot dot. Well, that's some kind of expansion. What's f of I? That's just 1 over 2i, right? Plus terms with at least a z minus I. So if I look at f of z, this is z minus I to the -1 times 1 over z plus I. So when I look at the Taylor series expansion about this, about z equals I, is it hard to calculate the Taylor series expansion of 1 over z minus I at I? What is the Taylor series expansion of this at I? So what is the Taylor series expansion? And again, I can have negative terms as well. What is the series expansion? It's just that, right? Remember earlier today I said I was thrown in my freshman math class because the answer was by definition. I'm giving you a one-term Taylor series. Sometimes people say Maclaurin series because it has a negative coefficient. I like to be inclusive and let Taylor refer to anything. It's just 1 over z minus I. There's nothing to do. So if I want to find the series expansion of the whole thing, I have the series expansion of this times the series expansion of that. So I get 1 over 2i, 1 over z minus I, plus a holomorphic in z minus I. You know, all non-negative indices. Because when you look at what goes on here, when I multiply this by 1 over z minus I, that's my whole. That's my residue. It's coming from that piece. The next piece, I'm going to have a z minus I times z minus I. That's going to just give me a constant term. Then I'll have a z minus I squared times 1 over z minus I. That's going to give me a z minus I. So what we can now do is we can calculate the residue at the point I of my function f is just going to be 1 over 2I. And we found a really simple way to calculate the Taylor series expansion. All right, so now let's go back to what we're trying to do. We want to find the integral from 0 to infinity of 1 over 1 plus x squared dx. We have to choose what contour to take. So the contour I'm going to choose to take is the following. Okay, so here's my contour. Here is minus r, here's r. And now if I look at the function f of z is 1 over z squared plus 1, this function has two poles. One is at I, one is at minus I. The only one that's going to matter for us is which? I. Why? The other ones are on the contour. So by Cauchy, if we call this something gamma, the integral over gamma of f of z dz equals 2 pi I times the residue at I of f. And what's the residue of I at f? It was 1 over 2I. So it's 2 pi I divided by 2I, which is pi. Okay, so now we have three pieces. Okay, let's call this gamma 1, gamma 2, gamma 3. And let's calculate what the contribution of the three pieces are. So we have gamma 1, gamma 3, gamma 2. We're taking a semicircle of radius r, here's the point I. So let's look at the integral over gamma 1 of f of z dz. Well, that's just the integral from 0 to r of 1 over 1 plus x squared dx, because we're just going along the real axis. So over here, z equals x. On gamma 2, we have the absolute value of f of z is going to be less than or equal to 1 over r squared minus 1. And this is what we said before. The worst case for us is when z squared is negative, because you have the negative real number from that plus 1. But if you think about it, 1 over z squared plus 1 among friends, about how big is 1 over z squared plus 1 among friends? Oh, a little bit better than 0. Yeah, it's 1 over z squared. Among friends, we can just drop that pesky little plus 1. So it's roughly 1 over r squared. So the integral along gamma 2 of f of z dz is going to be less than or equal to the maximum value times the length. And that's going to be less than or equal to 1 over r squared minus 1 times 2 pi r. And that goes to 0 as r goes to infinity. So the contribution of that part is going to be small. And now we're just left with the integral over gamma 3 of f of z dz. And now let's think about what's going on here. And this is where things get interesting. So our function is 1 over 1 plus z squared dz. We're on gamma 3. And on gamma 3, we go from minus r to 0. Right? So what we could do is we could change z to basically negative x. And then dz would become negative dx. And the negative sign switches the order of integration. So this would then become the integral from 0 to r of dx over 1 plus x squared. What we're really using is the fact that negative x squared is x squared. And that's why we chose this path. And so when we put it together, we get the integral from 0 to infinity of dx over 1 plus x squared times 2 was equal to pi. Therefore, the integral from 0 to infinity of dx over 1 plus x squared is pi halves, which agrees with what we did before. So I just want to end with, if we took n equals 3, the path you would want to take would be this path. And now we would take f of z is 1 over z cubed plus 1. And if we let zeta 3 be e to the 2 pi I over 3, this is a third root of unity. Note that zeta 3 of x cubed is just x cubed. And that's why when we come down along this path gamma 3, it's going to just give us another copy of gamma 1. So the details of that are done in the video. If I wanted to do n equals 4, it would be this path. And so on and so on and so on. And so the question is, can you reduce it so that you always have just one pole inside your region? And if that's the case, you just have to find one residue and you can get all the answers. And so this is how you get a really nice closed form solution. I will just end by quickly showing what that solution is. And we'll call it a day. And so it's pi cosecant of pi over n over n. So really, really nice answer at the end of the day. All right, so this is a good place to stop.